So welcome to everybody. Today we have Alessandro Scagliotti, who will talk about deep learning of diffeomorphisms via linear control systems. We recall that this series of seminars is a series of seminars taught to be for a broad audience. So maybe so for people who don't study necessarily the same topic of the speaker.
Okay, thank you very much, Sarah, for the introduction, and thank you very much for being here. So I'm going to talk about deep learning architecture obtained as a discretization of a linear control system. So in particular, in this talk, we will focus on the so-called residual neural networks that are particular architectures that can be interpreted as discretizations of continuous time control systems. Okay, so let's start by saying what is a residual neural network. So in our framework, a residual neural network is nothing but a mapping file from Rn to Rn, which is given as the composition of capital N elementary mappings. So each of these mapping phi k has the same structure. So it is given as the identity function plus a parametric function depending on a parameter u. Okay, here we have that the function capital F is assigned, and together with the number of the layers, capital N is part of the network architecture. While the parameters UN should be properly set or learned during the training process. Okay, so these kind of architectures are called residual neural networks. So now I'm going to tell you a fundamental observation that basically bridges the word of residual neural networks with the word of control theory. Indeed, if we look at one of those elementary mappings, we immediately realize that it is an explicit Euler discretization of a parametric dynamical system. So in particular, this is the dynamical system that is essentially discretized in an elementary function. Okay, this kind of dynamical system in which we have a parameter that can be set instant by instant are called control systems. And the function that instant by instant specifies the value of this parameter is called the control. Okay, this very simple observation was done independently in 2017 by Haber-Utot and by Wayne and I, and essentially it bridges the word of residual neural networks and more generally of deep learning with the word of optimal control theory. Okay, so let's explore this parallelism deeper. So essentially we have that in the residual neural network, the time is discrete, and essentially it is parameterized by the so-called layers of the networks. On the other hand, the control system is a continuous time dynamical system, and therefore the time takes value on a compact interval 0 capital T. Then we have that the key ingredients of the residual neural networks are the elementary mappings phi k, while in the control system, the key ingredient is the parametric dynamical system. Moreover, we have that in the residual neural network, for each layer, we have to specify the value of the parameters, and we have to do the same instant by instant in the control system. Okay, usually in the control system, we ask that the control, so the function that specifies the value of the parameter, has some Lebesgue regularity. So common choices are L2 or L3. Okay, moreover, the object of interest in the case of the residual neural network is the composition of the capital N elementary mappings. While in the control system, the object of interest is the flow induced by the system. Indeed, it turns out that once we have decided a control, we obtain, we have no more a parametric dynamical system, but we actually have a non-autonomous dynamical system. And we know that we can associate to a non-autonomous dynamical system a flow. Okay, in this case, it is important to remark that I'm not interested in the full flow, but I'm just interested in the flow at the final instant. So the flow can be seen essentially as a movie of describing the evolution of the dynamical system. So I'm not interested in the full movie, but I'm just interested in the final snapshot. Okay, so what are the consequences of this parallelism? First of all, the fact that the expressivity of the neural network is strictly linked to the controllability of the system. Then we'll explain what is the controllability of a system. And therefore, the process of training the network is strictly linked to the notion of to the resolution of a proper optimal control. Okay, so from now on, we will be interested in the task of approximating diffeomorphisms. So why diffeomorphisms? Well, the fact is that once we have decided an admissible control U, it turns out that the flow at the final instance, so the object of interest, is itself a diffeomorphism. So the idea is that we want that the family of diffeomorphisms that we can produce by choosing different controls form a rich enough family. What does it mean, rich enough? Well, it means that this family has nice approximating properties on the space of diffeomorphisms. So if it is the case, therefore, therefore we have that the residual neural network will inherit this expressivity, because, as we have seen, the residual neural network is an explicit Euler discretization of the dynamical system. So therefore, why? So this is the reason why it is so important to study the diffeomorphism approximation capability of the dynamical system underlying the residual neural network. Okay, so before proceeding to the residual neural network that we focused on, I present a popular form of residual neural network. So very popular residual neural network has typically this form. So the elementary mappings phi k are given as the sum of the identity, as we have already seen, plus sk, where sk is an n times n matrix that multiplies the output of the sigma. Okay, sigma here is an activation function, it's a smooth activation function. So it is not important to say what is an activation function, it is important to say that it is a nonlinear function. Moreover, the argument of sigma is an affine transformation of the x variable. Okay, globally, the dependence of phi on the parameters is nonlinear with respect to the parameters w and d. That is the take-home message. Okay, the first explored control system inspired by residual neural network had basically the corresponding structure. The only main difference is that the control that is found in front of the function sigma is often a scalar instead of being a matrix, but the other terms are exactly the same. Okay, so in 2020, Tabuada and Galiscott proved that the flows generated by these kind of dynamical systems can approximate monotone real analytic functions from Rn to Rn. So this is exactly one of those nice approximating results for diffeomorphisms that we are interested in. Okay, now we switch to linear control systems. So we focus on control systems that are linear with respect to the controls. Essentially, linear control systems have this form, and they can be seen essentially as the superposition of m different vector fields f1, fm. Each of them is weighted instant by instant by the corresponding control ui. Okay, we can also use this abridged notation in which the function capital F is an n times m matrix, and u is the vector of the controls. Okay, so what are the purposes? The idea is that before deciding if it is worth working out a residual neural network from this dynamical system, we have to study the approximating property or properties of the diffeomorphism of the diffeomorphisms that we can produce through this control system. Okay, so the results that I'm going to tell you were obtained between 2019 and 2020 by Agrachov and Scagliotti. Okay. In these results, in these approximating the results, an important role will be played by these technical property. So we will ask that the controlled vector fields F1, Fm that form the linear control system satisfy this condition, the Lie algebra strong approximating property. So I'm not going to tell you what is this condition because it's quite technical. I'm just going to tell you that if you want that this condition holds, you have to include this family of vector fields among the controlled vector fields F1, Fm. Okay, so if it is the case, then the Lie algebra strong approximating property holds. Okay, so now let's simplify a little bit the notations and let's start talking about controllability. Okay, so we are dealing with a linear control system and we can reduce without loss of generality to the time interval 0, 1 instead of a generic time interval 0. Okay, it is done just by rescaling the controls. Moreover, we simplify a little bit the notation for the Diffeomorphism, so we drop the notation 0, 1. So given an admissible control U, we simply denote by phi U the corresponding flow at the final instant. Okay, now we have the controllability problem. What does it mean, controllability problem? So let's choose any 2 points, x1 and y1 in Rn. We have that x1 will play the role of starting point and y1 will play the role of target point. Okay, the problem now is to find if exists an admissible controller U bar such that the corresponding diffeomorphism phi U bar maps the starting point x1 onto the target point y1. Okay, if it is possible for every choice of the initial point x1 and for every choice of the target point y1, we will say that the system is controllable. Okay, let me say that this controllability property is a very classical problem, and it should be the first question that you ask when you're dealing with a control system, both linear and nonlinear. So it is a very classical and studied property, and therefore the question to the answer to this question is very classical. So the system is controllable if the family of vector fields F1 Fm is Lie bracket generating at each point. What does it mean? Okay, now it is not so important. It is just important to say that this condition is implied by the Lie algebra strong approximating property. Okay, which is the technical condition that we require to our vector fields. Okay, so now same notations as before. We are talking about a much more complicated controllability problem. Okay, I'm using exactly the same notation as before, but now the problem is much harder. Okay, for every m, I consider an ensemble of initial points x1, xm, and an ensemble of target points y1, yn. All the initial points and all the target points are different from each other. Okay, now the problem consists in finding an admissible control, if it exists, of course, such that all these identities hold simultaneously. Basically, it means that the desired diffeomorphism should map each initial point onto the corresponding target point. Okay? Of course, this condition is much harder than just the controllability because the larger is M, the larger is the number of identities that must hold simultaneously, and so therefore the harder is the problem. Okay, if for every m greater or equal than 1, and for every choice of initial point of the initial ensemble and of this target ensemble, we can do this job, we will say that the system is ensemble controllable. Okay, now the sufficient condition for the ensemble controllability is exactly the Lie algebra strong approximating property. Okay, just to wrap up, we have that if the Lie algebra strong approximating property holds, we have the exact controllability for finite ensembles. So we have that given an initial ensemble of points and given any target ensemble of points with the same cardinality, there exists a diffeomorphism generated by the linear control system that maps the initial ensemble onto the target ensemble. Okay, we have something more. Okay, still under the Lie algebra strong approximating property, we have that given a diffeomorphism psi isotopic to the identity, for every compact set and for every epsilon positive, there exists an admissible control such that the C0 norm between the diffeomorphism psi and the approximation provided by phi u bar is less or equal than epsilon. Okay, before proceeding, let me just say what is a diffeomorphism isotopic to the identity. Well, essentially, it is equivalent to say that is a finite time flow of another dynamical system. So the idea is that if the V algebra strong approximating property holds, then we can approximate the flows produced by any other dynamical system, at least on compact set. So this is an important condition. So we can approximate on compact set the action of an arbitrary dynamical system. Okay, so we have this condition, which is exactly the diffeomorphism approximation condition that we were looking for, and now we need to design a training strategy for the approximation of a diffeomorphism. From now on, the state, we will assume that our controls belong to the have L2 regularity. I just recall that since we are dealing with a compact time interval, L infinity is of course included in L2. Okay, so before proceeding, I'm presenting you the first strategy that we may come up with, which is of course which in general does not work. Okay, so the problem here is that we have a psi, which is a diffeomorphism isotopic to the identity. The task is to approximate the psi on a compact set of Rn, and the approximation will be data driven. So we assume to observe the action of psi on an ensemble of points sampled in the compact set. Okay. With this observation, we may define the target ensemble, Y1, Y2. Okay, so what is the first idea we may come up with? Okay, the idea is that we could use the exact controllability for finite ensemble in order to produce an approximation. The idea is that since we can approximate exactly the finite ensembles, we can obtain an admissible control U bar M such that the corresponding flow phi U bar M maps each initial point onto the observed image. Okay, so with this strategy we achieve a null training error, but of course in this strategy there are a lot of drawbacks. For instance, to say one of them, the observation of psi may be affected by error. So in that case, it is not a good idea to reproduce exactly the observations. But what is even worse is that with this strategy, we have no bound on the generalization error. What is the generalization error? Well, it means that the error that we commit outside the observed points. So we know if we reproduce exactly the observations, we know that on the trailing points, the approximating diffeomorphism is doing exactly as the diffeomorphism that we want to approximate. The problem is that we have no control on what happens outside of these points. Okay, so basically we have to change this paradigm. So instead of trying to achieve a null training error, we have to introduce a functional and to look for a trade-off between the training error and essentially the simplicity of the approximation. Okay, what does it mean? It means that we define a functional Fm on the space of the admissible controls. The first term essentially takes into account the squared error, the discrepancy between the observation and the approximation produced by our diffeomorphism. The second term is a penalization on the L2 norm of the controller. Okay, this second term is essentially an Occam razor for the approximation. So the idea is that we do not want too much complicated approximation for our data. We want to find a trade-off between a good approximation and a simple enough approximation. Okay, this is more or less the idea. Okay, before, so with the poor training strategy, the training was seen as a purely controllability problem. Now it is seen as an optimal control problem because we have to minimize a functional defined on the space of admissible controls. Okay, so before proceeding, in order to show you the bound on the generalization error, I need to tell you something about a gamma convergence result. Okay, what does it mean? So as we have seen, the approximation of the diffeomorphism psi is data-driven because it is based on the observations of the action of psi on an ensemble of points. Okay, we may assume that the ensemble of points x1 xm are sampled using a probability distribution on the compact set K. Okay, so let's denote by mu m the empirical distribution associated to the observations. Okay, we just rewrite the functional fm using this empirical probability measure in place of the summation, and the functional is exactly the same. And now I'm going to present you the gamma convergence result. Okay, what does it mean, gamma convergence? Okay, the gamma convergence is nothing but a stability result with respect to the number of training points. So the question is the following. So let's assume that we have a billion we have observed the action of the diffeomorphism on a billion of points, and then we repeat the approximation with 1,000,001 points. What do we expect? Of course, we expect that the two approximations, will be very, very similar. Okay, this is essentially the content of the gamma convergence result. The fact is that the sequence of the functionals fm is gamma converging to a functional f infinity, where f infinity has essentially the same form as the functional fm, but the measure that we use to do the integral is not the empirical measure, but is the measure that generates the sampling. Okay, what does it mean? Essentially, it means that the sequence of the minimizers of the functionals fm are pre-compact and are converging to the minimizer of the functional f infinity. Okay, that matches with the intuition that an approximation with 1 billion point and 1,000,001 point should be similar. Okay, moreover, this gamma convergence result as a byproduct implies an estimate on the expected generalization error. Essentially, we can find an upper bound for this quantity. The expected generalization error is the mean squared error that we commit by approximating the unknown diffeomorphism psi with the diffeomorphism obtained by using as a control the minimizer of the functional fm. Okay, so now we have the strategy, the correct strategy, we have the correct estimate, and we want to actually minimize the functionals fm. Okay, essentially I'm going to present you two approaches. The first one is based on gradient flow, because essentially we have a function fm that induces on the domain a gradient flow, and we can use this gradient flow to find a minimizer. And a second approach is based on an iterative method based on the Pontiacki maximum principle. Okay. Of course, the construction of the residual neural network takes place at this stage. Indeed, in order to solve numerically the optimal control problem, we have to discretize the control system. And I recall you that if we use the explicit Euler method to discretize this system, we end up exactly with one of those elementary functions. I just recall you that I'm using the abridged notation for the linear control system. Okay. So in both the approaches, an object that will be crucial is the adjoint variable. Okay, what is the adjoint variable? In few words, the adjoint variable is a curve in Rn to the power n. I just recall that Rn is the ambient space. So basically where lives the diffeomorphism that we are interested in. and capital M is the number of training points. So essentially, we have an adjoint variable for each training point. Okay, these curves, these adjoint variables, satisfies this differential equation, which is linear with respect to lambda, and the Cauchy datum is assigned at the final point. Okay, it is not important to understand the dynamics of this differential equation. The only important thing is that the computation of the adjoint variable by solving this backward Cauchy problem is the continuous time equivalent of the back propagation. Okay. So essentially, now I can just tell you the statement of the gradient flow approach, which is essentially the fact that the differential of the function Fm can be represented as an element of the Hilbert space of the admissible control. Okay, I'm not insisting on this result. I'm just telling you that the first term here in the gradient flow descends from the training error cost, while the second term derives from the L2 regularization cost term. Okay, basically we can introduce this gradient flow, and we can let the system evolve in order to obtain a minimizer. Okay, in practice, what do we do in practice? So essentially, we approach the problem with a finite dimensional, with a finite element approach. So essentially, we approximate the space of controls U with a finite dimensional approximation UN, and we projected the gradient flow onto this finite dimensional approximation. Okay, in particular, we introduce a uniform discretization in the time interval 0, 1, and we consider the controls that are constant in each subinterval. Okay, so and now I'm just going to tell you which are the phases of this algorithm. So these are okay. I'm just going to ask you to keep in mind these three phases. So in the first phase, we perform the computation of the trajectories. In the second phase, we perform the computation of the adjoint variables. And finally, we perform the update of the controls. Okay. So now this is a technical slide. In order, if there will be some detailed question regarding this algorithm. Okay, so now I'm going to telling you the second approach, so based on the Controllability maximum principle. So the Controllability maximum principle is essentially are the necessary condition for minimality in optimal control problems, and are more or less equivalent to the Euler-Lagrange equations for calculus operation. Okay, what is the statement? The statement is that, okay, let's assume that U tilde is a minimizer for the function Fm. Therefore, we can consider this differential equation that provides the trajectories obtained by evolving the initial ensemble through the dynamical system provided by the choice of U tilde, and we consider the corresponding adjoint variables. What is very important, the core of this slide, is the very last part. Okay, in the very last part, we deduce that the value of the admissible control is obtained by of the minimizer is obtained by maximizing this object. Okay. Now, the only important thing that I would like you to keep in mind is that the maximization of this object, which is called Hamiltonian, is extremely simple if the system is linear with respect to the control. In this case, in the case of linear control system, this maximization process can be solved exactly at an extremely low computational cost. So that's why this is essentially the numerical reason why it should be interesting to study this kind of linear control systems. Okay, so now the numerical algorithm based on the Controllability maximum principle. Okay, the method that we employed was suggested in the 1980 by Sakawa and Shindo, and this method was essentially a stabilization of a method that was already known in the Soviet literature. So in 1982, there is an English translation of a review paper. Okay, anyway, the framework more or less is the same as before. So we introduce a uniform discretization of the compact time interval 0, 1, and we consider controls that are piecewise constant. What changes now are the phases of the algorithm. So it consists only in two phases. In the first phase, there is the computation of the adjoint variables. And in the second phase, there is the joint computation of the trajectories and the update of the control. So the computation of the trajectories and the update of the control take place simultaneously. Okay, and now I reported the technical slide for in case of questions. Okay, algorithm comparison. Oh, okay, what are the differences between those two approaches? Okay, basically the difference is captured by this analogy. The gradient flow method is similar to the Jacobi method for the resolution of linear systems, while the maximum principle is similar to the Gauss-Seidel method. Okay, what do I mean by this comparison? Okay, the fact is that the amount of computation per update is comparable for these two methods. In the maximum principle case, we have a faster convergence per iteration, but the problem is that it is the algorithm is non-parallelizable. In the case of the gradient flow, we have a slower convergence per iteration, but this algorithm is highly parallelizable. Okay, so finally, I reported a numerical experiment of diffeomorphism approximation. Okay, we have that. The red dots here represent the initial ensemble, and the blue dots represent the transformed ensemble, the ensemble which has been transformed through an unknown diffeomorphism. Okay, this is the approximation provided by the gradient flow method. Okay, I run 100 iterations, and this is the result. On the left, there is the training approximation, and on the right, I tested the approximation of on an unknown ensemble of a new ensemble of points. Okay, the approximation is quite good, of course, where we have more data, where it is less accurate, where the data are more sparse. Okay, now here we have, on the other end, the approximation provided by the maximum principle. Okay, I run also in this case 100 iterations, and as you may see, in this case, the approximation is better than the one provided by the gradient flow method, and this is essentially due to the fact that the per iteration decrease is the per iteration decrease is higher in the algorithm involving the maximum principle. Okay, so thank you for this.
Thank you, Alessandro, for your seminar. Are there any questions?
And the last two graphs. The red dots and the blue dots are the function in the diffeomorphism we want to approximate.
Exactly right. The red dots, this is in the maximum principle case. So the red dots, so if we look at the left-hand side one, so the blue dots are the same as in this slide, so are the same blue dots as before, and are is essentially the target ensemble. So are the points are the y1, yn. So are the points that has been transformed through the unknown diffeomorphism. While the red dots are the
Alessandro, excuse
me.
I've lost the connection, and my question was exactly if you can explain a little bit better the dots. So please, can you repeat the answer? Sorry.
No problem. Okay.
Thank you.
Okay, I was saying that. Okay, let's begin. Okay, let's start from here, which is the okay. In this case, we have that the red dots are the training points where we observe the unknown diffeomorphism, and the blue dots are the transformed points through the unknown diffeomorphism. So these basically are the training data set. Okay, then we have, for instance, here, these in the case of the gradient flow method. Okay, the blue dots are on the left-hand side are the same as before. So are the transformation through the unknown diffeomorphism of the initial ensemble. In this picture, the red dots are the approximations provided by the approximating diffeomorphism. Okay, on the right hand. Okay. This is the same for the picture for the left-hand side picture of the maximum principle. Okay, the blue dots are the transformation of the known diffeomorphism on the same data set, while the red dots are the approximations provided by the transformation provided by the diffeomorphism approximated by the maximum principle algorithm. Okay, in this case, the approximation is better than before because of the per-iteration decrease is better. I hope
Sorry, and the testing.
In the testing, okay, the testing points are different from the two algorithms. So in the testing point, I essentially taken some new initial points. Okay, and I have transformed them through the unknown diffeomorphism, obtaining the blue crosses. Okay, and then I did the same with the approximated, the diffeomorphism provided by the approximation, and I obtained the red crosses. Okay, so this testing phase is useful to understand if you have done a good job only on your training data, or you are doing a good approximation also outside your training data.
And you generated both with the same distribution?
Yes, yeah, exactly right. I generated both the testing data and the training data and the testing data with the same distribution. Yes, of course. Yes, the idea is that I expect to find a good approximation here in this compact here where I have observation. Actually, the approximation that we can provide is not expected. For instance, produce good approximation of the diffeomorphism in a region where I have no observations. Okay.
Thank you, Alessandro.
Welcome.
I mean, I have a lot of comments actually. It's a very good talk. Thank you. I always like your talks, Alessandro, because they are a good bridge between our interests, I think. You showed us basically that gradient flow is a Jacobi method, and the Pontryagin maximum principle is something like Gauss, right?
Yes.
But are there other techniques that you can, I mean, you showed us only two of them because there are only these two ways to go, or there are also other techniques?
Okay. This is a good question because finding numerical methods for optimal control problems seems, at least to me, quite hard, because the method that at the end of the day used for the maximum principle approach was proposed in 1980, but it seems that is at least this paper. It seems that is not so much known. Actually, the answer to your question is that I actually don't know if there are many other numerical algorithms for this kind of problems. On the other hand, the gradient flow method essentially we obtain it from the theoretical result of the well-posedness of the gradient flow equation on the phase of on the space of admissible controls. Unfortunately, as far as I know, there is not the same richness of methods that we have in computational linear algebra.
Okay. Yes, of course. I mean, the structure it's more complicated, you know, and it's always a mess. And I mean, I had another question in mind, but now I totally forgot. My God. No, I forgot. I forgot the question, Alessandro. Maybe it was not important.
Maybe regarding the algorithm, regarding...
No, it was in the beginning. Yes, okay, because basically on, you know, Google or Microsoft Teams, there is this bar and you cannot see, you know, the convergence of your gamma convergence theorem and
Okay.
yes, so yes, the slide that you had, like with the kappa something. Yes, I cannot see the
This one or...
Okay, here. I mean, I was wondering, you know, all this stuff, how is it related with respect to the training or the number of layers? I mean,
okay, well,
because I don't see it right now. Like beta, you choose something like beta 10 to the -5. That is very small, right?
yes.
So basically, you can control a lot your system, and basically, I think that you can somehow have a faster convergence or something like that.
Yeah, I've chosen beta very small. So beta is is the parameter that weights L2 regularization.
Yes, exactly. That means that basically, L2 regularization. Okay, no, I was wondering because in optimal control, you know, beta means that if beta is small, you can control a lot your system somehow because it doesn't weight a lot on your functional. So the norm of U can be high. If you think
exactly right, yeah.
Okay, great.
Yeah.
So I was wondering how the algorithm basically works for different kind of beta and how it affects.
I can show you the technical slide for implementation. Okay, essentially you can see the action of beta here in the principle-based algorithm. You essentially have that when you update the control, you have to maximize the discrete Hamiltonian. Okay, and essentially the role played by beta is here. Okay, I suspect that the fact that I can choose beta very small is in part linked to the fact that the system is ensemble controllable. So in theory, I can send the finite ensemble exactly onto the target ensemble. And this is one point. But the second point is that part of the regularization of the L2 regularization is given by this second term. Second term, essentially, when I maximize, for all of you who know what I'm meaning, it is a minimizing movement. In other words, when I maximize this guy, I'm just doing an implicit Euler update okay, so let's look at the Hamiltonian without the very last term. Okay.
Okay.
In order to maximize this, basically, in order to maximize this, I can take the gradient of this guy and perform an explicit Euler update. The second approach is to add this very last term and maximize this term. If I do that, it is equivalent to do an implicit Euler step, an implicit Euler discretization of the gradient flow equation.
Okay.
Okay. And what is the partial answer to your question is that I think that I can take beta very small because part of this regularization is provided by the very last term.
Okay.
Because if in order to maximize this one, the value of U cannot be too much large.
Okay. So somehow U is controlled by
This method, this discretization is intrinsically robust. I would.
Okay. I mean, this part of the algorithm, in your opinion, actually controls the control.
Yeah.
Somehow. Okay.
Control. Yeah. Exactly.
Okay. Great. Thank you.
Eta is the learning rate, is the step size that you use to update the controller. So yeah, the idea is that when you maximize the Hamiltonian, you don't go from one point to the maximum of the Hamiltonian, but you are quite conservative. You say, okay, this is the maximum of the Hamiltonian, but I don't go directly there. I just go quite closer to the maximum of the Hamiltonian. And the eta quantifies how much you are conservative. The smaller beta, the more you are conservative, in some sense.
Thank you, Alessandro.
Very welcome.
Are there any other questions? Okay, so if not, we can thank Alessandro again.